Started recording. Okay. Okay. In the last class, we discussed about. So in the last class, we discussed about contravariant and covariant vectors. So let us try to recall that. What is a contravariant vector? Suppose I have a vector v, and if this vector is a contravariant vector, then the components. So if this is a contravariant vector, then the components of this vector, they transform according to the rule vi prime is equal to dou x I prime by dou xj vj. Okay, so what are vj's? Vj's are the components of the vector in the unprime frame, and what are vi prime? Vi primes are the component of the same vector in the prime frame. Okay, so if the components of the vector vj it transform according to this rule, then we say this is a contravariant vector. Okay, similarly, we had a similar definition for covariant vector. Okay, so if v is a covariant vector in such a case, so okay, let me write it here. If v is a covariant vector in such a case, we here in covariant vectors we use subscript. In contravariant vector we use superscript. So this is dou x. Sorry, this would be xj. Okay, so let me try to undo it. Okay, so this would be dou xj by, okay, I'm using I here, so this would be xj by dou x I prime. Okay, dou xi prime vj. So this is the covariant vector, and this is a contravariant vector. So the first equation tells us, so this equation tells us how the components of a contravariant vector transform under a coordinate transformation from the unprime frame to the prime frame. Similarly, the second equation, this equation number 2, this is equation number 1. The second equation, this equation tells us how the components of a covariant vector transform under a transformation of coordinates from the unprime frame to the prime frame. Okay, this we saw last time. Okay, and here we see that we have xj here and vj here, so one index is repeated. This means we are using the summation convention. So here we are using the summation convention. Summation convention is being used here. Okay, so that is fine. This I think we discussed in our last class. Okay, then let us move to tensors. So this is a contravariant vector. Okay, this is a contravariant vector and this is a covariant vector. Okay, and I mentioned in the last class that vectors are actually tensors of order 1. Okay, I repeat, vectors are tensors of order 1. Okay, now how about tensors of higher orders? Okay, so tensors of higher orders. Let us come to tensors of higher orders. Okay, so tensors may be covariant of any rank, contravariant of any rank, or they may be mixed. So let us look at some examples. So first, let us look at a second rank covariant tensor. So the second rank covariant tensor, this is Tij. Let us call it Tij. And let us see how it transforms under a coordinate transformation from the unprime frame to the prime frame. Okay. Here we go. So this means here we'll have dou xk, dou xi prime. Okay. Similarly, dou xl, dou xj prime, t k l. So I have a quantity t represented by t, and this t has many components. And if the components of this tensor t, if they transform according to this rule, then we say that this t is a second rank covariant tensor. So this is second rank covariant tensor. Covariant tensor. Okay, so this is easy, and we can have similarly a third rank covariant tensor and so on. So now let us look at the contravariant tensor. Okay, so this t prime and I j k. This will actually be a third rank contravariant tensor. So we can write it like this. This is dou xi prime divided by dou x, we can call it L. Similarly, dou xj prime. Oh, I can use the prime before the index or after the index. This is fine. J prime divided by dou xm, dou xk prime divided by dou xn, and t l m n. Okay. So if the components transform according to this rule, then we say that it is a third rank contravariant tensor. Contravariant tensor. Okay. So this is how the components of a third rank contravariant tensor transform. Next, let us look at a mixed tensor. Okay. So mixed tensor. So it would be something like this. T prime, this is T prime, I, J, K. It is like this. Okay, let me move my T prime I, J, K. This is equal to, oh, sorry. So this is equal to, so we have two superscripts and one subscript. Okay, these two superscripts would correspond to contravariant part, and this subscript would correspond to covariant part. Okay, so this would be dou xi prime by dou xl. Similarly, dou xj prime by dou xm. So far, these two cases, they are the same. Now, if we look at this case and this case, now k has moved to the subscript. So the transformation rule should change. So this will be dou xn by dou xk prime. And t, this would be L, M, N. This is a third rank mixed tensor. Third rank mixed tensor, and we have one covariant index and two contravariant index. So we have one covariant index and two contravariant indices. Okay, So I'll pause my recording here. Now let us try to remember our Kronecker delta. Kronecker delta. And we saw earlier that this Kronecker delta, that is delta ij, is a second rank tensor. Second rank isotropic tensor. Isotropic Cartesian tensor. Cartesian tensor. And you remember we kept both the indices as subscripts. Okay. Because in Cartesian coordinate systems, there is no distinction between covariant and contravariant. So we can keep both the indices as subscripts. But once we move towards general tensors, then there is a difference between subscript and superscript. Subscript indices we use for contravariant tensors, and superscript indices we use for, superscript indices we use for contravariant tensors, and subscript indices we use for covariant tensors. So in the formalism of general tensors, there is, in a general coordinate system, the second rank tensor, which is equal to 1 when the indices I and j are equal, and is equal to 0 when I and j are not equal, is actually a mixed tensor. So in a general coordinate system, the Kronecker tensor is actually this delta with one index up and one index lower. Okay, so the Kronecker delta tensor, this is actually a mixed tensor. Okay, this is a mixed tensor of order 1, 1. Sorry, type of order 2 or rank 2 and type. So let me write this as its rank is 2 and its type is, how many contravariant indices are there? There is only one contravariant index, so it's type 1. How many covariant indices are there? There is only one covariant index, so 1. So delta ij in the formalism of general tensors is actually a rank 2 type 1, 1 tensor. We call such tensors mixed tensor. Mixed tensor. Okay, so if we move to, okay, here in our last slide here, we saw that this is a mixed tensor. Okay, so this is a mixed tensor. Okay, with covariant index and contravariant index. So similarly, in the formalism of general tensors, delta ij is actually a mixed tensor. Okay, and this delta ij, this delta ij, this is equal to 1 if I is equal to j, and this is equal to 0 if I is not equal to j. Okay. So how can we show that delta ij is a mixed tensor? Okay, to show that delta ij is a mixed tensor, let us see how delta ij transform. Okay. I repeat, let us write down the tensor transformation equation for delta ij. So the transformation equation is this: dou xi prime divided by dou xk dou xl divided by dou xj prime. J prime, dou k and l. Okay. This is the transformation equation for delta kl when we move from the unprime frame to the prime frame. Okay. Now let us look at one of the indices. So let me change the color here a little. Here, let me change it to green. You see this index L and also this index L. So in this expression, the index L is repeated. That means we are using the summation convention. Okay. Let me pause my recording. So we see that in this particular term, this index L is repeated. That means we are using the summation convention. Okay. So now if I combine these two, terms, what should I get? I should get this expression. So this should be equal to, the first term remains unchanged, xi prime by dou xk. But the second term, here L has been contracted. So L will be replaced by k. So we have dou xk divided by dou xj prime. Okay, so this is the expression which we will get. Now again, you will see that here we have one index k. So let me change the color again. So here we have one index k and another index k that is summed over. So we are still using the summation convention. So if I combine these two expressions, what should I get? I should get dou xi prime divided by dou xj prime. Okay. And what is this? This is nothing but delta prime ij. This is delta prime ij. So we see that under a coordinate transformation, delta KL transforms to delta prime ij. Okay. And delta KL, what are the components of delta KL? The components of delta KL are this. When K and L are equal, it is 1. When K and L are not equal, it is 0. Okay. And what is the final transform tensor that we get? We again get delta prime ij. And what are the components? If we look at this expression, we'll see that if I and j are equal, then it will be equal to 1. And if I and j are not equal, then it will be equal to 0. Okay. So this means that this delta ij, so this actually means that delta ij is actually an isotropic second rank tensor. This is actually a second rank mixed tensor in general coordinate system. In general coordinate system. Coordinate systems. Okay. So if you want to prove that delta ij, which is a mixed tensor, that is this tensor. If you want to prove that this tensor is a mixed tensor and it is an isotropic tensor of rank 2, then you simply need these steps to prove that delta ij is a mixed isotropic tensor of rank 2. Okay. So that is all about Kronecker delta. And we can also see that, let me move it a little. We can also see that our epsilon I, j, k, or permutation tensor, which was a tensor in Cartesian coordinates, that is, we saw that this is actually a Cartesian tensor. Cartesian tensor. That is, this behaves like a tensor when we transform coordinates from one Cartesian coordinate system to another Cartesian coordinate system. But the next question is this a general tensor? Is epsilon ijk a general tensor? That is, under a coordinate transformation from one curvilinear coordinate system to another curvilinear coordinate system. Does this transform like a tensor? The answer is actually no. So this is not a general tensor. Okay, we can show that epsilon ijk is not a general tensor, but it is a Cartesian tensor. We already showed that this epsilon ijk is a Cartesian tensor, but when we check whether it is a general tensor or not, we will see that it is not a general tensor. Okay, then let me. Here is one example, and what does it say? If AI and BJ are the components of a covariant and contravariant vector respectively, then the sum AI BI, then the sum AI BI is an invariant. That is, it is a scalar. Okay, to try to prove this, I'll give you the hint. So what will you do? You start with you can consider the equation of transformation of a covariant vector and a contravariant vector. Okay, then you try to prove this. A prime I B I prime. You try to prove that this is equal to AJ BJ. Okay, what is this? This is the component of, I repeat, this is the component of the covariant vector A in the prime coordinate system. This is the component of the contravariant vector B in the prime coordinate. And I have set their indices equal. That means we are using the summation convention. So this is actually A prime 1, B prime 1 plus A prime 2, B prime 2 plus A prime 3, B prime 3. And if we can show that this is equal to, this is AJ, this is the component of A, the covariant vector A in the unprimed system. This is the component of the contravariant vector B in the unprimed system. So this is A1 B1 plus A2 B2 plus A3 B3. So if I can show that these two are equal, the left hand side is equal to the right hand side, then our work is done. Then it simply means that AIBI is an invariant. Okay, so how will you show this? You expand this in terms of AIBBJs by using the transformation rule. Okay, by using the transformation rule, then you use the properties of partial derivatives and simplify this. Finally, you will get this expression. You try this. If you cannot prove it, then we'll discuss it tomorrow. Okay. So next we move to algebra of tensors. Algebra of tensors. Algebra of tensors. Okay, this is fine. So first, so what are tensor operations? Tensor operations, they are actually operations like addition, subtraction, multiplication. Okay, so how can we add tensors? How can we subtract tensors? How can we multiply tensors? This is all about algebra of tensors. This is what algebra of tensors mean. So first, let us look at addition and subtraction. So first, addition and subtraction. Addition and subtraction of tensors. Okay, so how can we add two tensors? And here I'm not talking about Cartesian tensors, I'm talking about general tensors. Okay, so here the rule is that the algebraic operation of addition or subtraction applies to systems of same type and order. That is, I repeat, the algebraic operations of addition and subtraction applies to tensors of same type and order. That is, we can add or subtract the like components in system. For example, if I have a tensor A, I, J, K. So this is a mixed tensor with one contravariant index and two covariant indices. Okay. To this tensor, I can add or subtract another tensor I, J, K. So this tensor A and B, they are of the same type. That means it has one contravariant index and two covariant indices. So these are tensors of type 1, 2. Okay. So these are tensors of rank 3 and type 1, 2. So type 1, 2, rank or order 3. Okay. So these are of similar types. So we can add these tensors. Yaraba. There you go. But if we have two different tensors, say for example, if I have another tensor, I, J, K. So if I have another tensor like this, what is the type of this tensor? This one type is, how many contravariant indices are there? Two indices. So type 2, 1. So the type of this tensor and the type of this tensor, they are not equal. So we cannot add these two tensors. We cannot add these two tensors. Tensor however. That is A, I, J, K plus C. Sorry, this would be this will be the last C, I, J, K. You see, these are two tensors, A and B. These are two tensors. Sorry, A and C. These are two tensors, but they are of different types. So you cannot add them. This is not correct. You cannot add such tensors. You cannot subtract such tensors. This is what addition and subtraction of tensors they tell us. This is the rule for addition and subtraction of tensors. Okay. Now let us move to multiplication of tensors. So let me change my sheet. So next is multiplication of tensors. So the second part is multiplication. Multiplication of tensors. Okay. And how is multiplication of tensors done? The multiplication of two tensors is obtained by multiplying each component of the first tensor with each component of the second tensor. That is by multiplying each component of the first tensor with each component of the second tensor Okay. And this multiplication, this product is called outer product. This is called outer product. This is called outer product. outer product of tensors. Okay. For example, let us look at one tensor that is A, I, J, K. So this is a tensor of type 1, 2. Okay. Now, if I multiply this tensor by another tensor, B, L, M. Now, BLM is of type 2, 0, 2, 0. Okay. So when I multiply these two tensors, I'll get another tensor. The resultant tensor will be like this. This will be C. So we have I, L, M, J, K. Then this is of type 3, 2. So Cij is of type 3, 2. This is of type 2. So in 3 dimensions, you tell me how many components does capital A have? This will be 3 times 3 times 3. Okay, 27. And B will have 9 components. Okay, this will be 27 times 9. Okay, so actually this will be 3 to the power 5. 1, 2, 3, 4, 5. 3 to the power 5. Similarly, here we'll have 1, 2, 3, 4, 5. So again, 3 to the power 5 components. Okay. So this is all about product of tensors. Fine. Then we learned about contraction of tensors. Contraction contraction occurs when a lower index is set equal to an upper index and then it is summed over. So for example, contraction of tensors. Suppose I have a tensor like this: C, I, J, K, L, M. Okay. Now, if I set two indices equal, say suppose I set I is equal to L. Let me set these two indices equal. So if I contraction means C, I, J, K. Now L will be replaced by I. Okay, I, M. So I am contracting L with I. So this means, so we have one repeated index. This actually means we are taking C11 JK M plus C2 JK JK, there is no M, 2M plus C3 JK plus 3M plus 3M. Okay, and this will give rise to a tensor whose rank is reduced by 2. So the earlier tensor, this earlier tensor, it has 1, 2, 3, 4, 5. 5 indices, so it has rank 5. And its type is 3, 2. But now after contraction, it has reduced to rank 3 and type 2, 1. Okay, so this is all about contraction of tensors. Okay, so I think I'll stop here for today, and tomorrow we'll continue with the quotient law, and then after that we'll discuss about metric, and then we'll stop. Okay.
Yes, sir.